Alright guys, just a couple more videos until I'm back with you, so let's just kind of continue on through this. So we left off on here, which is the start of Hess's law, and there's a couple different ways we can calculate using Hess's law. Remember, what we're talking about is calculating enthalpy, and so far we've talked about two ways to calculate enthalpy, which the first way is using our calorimetry, Q equals mc delta T, as well as using bond energy. Okay, so we can calculate it using calorimetry or bond energy. We can also calculate molar enthalpy if we're given an original enthalpy, so that's also part of the mix. Don't forget that. Now, we left off on here, which is using Hess's law, and two ways to calculate Hess's law. The first way is to take reactions and rearrange them to get our original reaction. So we looked at this one on the last video. So this is our original reaction. Here are two steps for this reaction. So remember, enthalpy is a state-wise function, or a state function, which basically means it doesn't matter how many steps it takes to get there, as long as the beginning and ending are the same. So remember our hiking example. So these are our two steps, okay, and we want to line them up so that they add together and cancel out to make this reaction, which we already did. We have our nitrogen on our reactant side, and we have our nitrogen dioxide on our product side, and we set it up so everything cancels out, so there shouldn't be anything left over that is not in our original reaction, and everything that is left over should be in our original reaction. So notice nitrogen monoxide, NO, is not in our original reaction, so we cancel it out. We should have nitrogen left over, we should have two oxygens left over, which add up here, and two nitrogen dioxides, which are this guy here. Once we have the reactions all lined up and ready to go, we add up, cancel out, and we do the same thing with our delta H's. So whatever we do to these reactions to get them to equal this reaction, we do the same thing with our delta H, because remember, delta H is an extensive property, meaning it depends on the amount. So let's say I flip this top reaction. What am I going to do with delta H? Well, I'm going to change the sign and reverse it. So I've got a positive 180. I would end up with a negative 180. Let's say I half my bottom reaction, meaning I change my coefficients to 1, 1/2, and 1. I'm going to half my delta H. So what if I flip the bottom reaction and double it? Well, I'm going to flip my sign and double my delta H. Whatever I do to my reaction, I do to my delta H. Once I'm done and everything adds up, so here's our added reaction, which matches our original, all I'm going to do is take my delta H's the exact way I worked through them, meaning if I doubled them, halved them, flipped them, whatever, and add them up. So let's look at a couple more and see what we can come up with. Okay, so two forms of carbon are graphite, the soft black silvery material used in lead pencils, and diamond, the brilliant hard gemstone using enthalpies of combustion for graphite, which is negative 394, and diamond, negative 396. Calculate the delta H of the conversion of graphite to diamond. So what exactly are we doing here? We're given the reaction here of graphite to diamond. So our reaction is going to be C, graphite, and I'm just going to call it CG, instead of writing it all out like here, going to diamond. Okay, which again, the D is representing the diamond. So we're going from carbon, graphite to carbon, diamond. And we're given these two reactions and these two delta H's. So what are we going to do to get this reaction? Well, first off, we're going to look at our reactants and products on both reactions that were given, our steps that were given, so step 1, step 2. And we're going to look at our total reaction. So this is a reaction we're trying to get. Notice graphite is a reactant, diamond is a product. Also notice oxygen and carbon dioxide are not in our final reaction, which means we have to get rid of them in our stepwise functions. Okay. First thing I'm going to notice is that carbon diamond is a reactant here, so I want to flip that reaction, and I'm going to turn it into carbon dioxide, going to oxygen and diamond. Okay. From there, what I'm going to notice is that these arrows, and I'm actually going to show you my trick here. What I do is I line my arrows up much like an equal sign. So if I have my arrow here, I'm going to have the carbon dioxide over here, and I'm going to have the C diamond and oxygen over here. So now what I'm going to do is recognize that anything on opposite sides of the arrow, so like carbon dioxide, they're going to cancel. They will only fully cancel if they are the same quantity. So both of these are 1 carbon dioxide, so they will both cancel. If I had a 2 in front of here, they would not cancel out completely. One would cancel out, but the other one would be left over. We'll look at one of those in just a minute. Okay, carbon diamond and carbon graphite are not the same thing, so they cannot cancel. Keep in mind, they also have to be the same state of matter to be able to cancel. So notice this is gas, and this is also gas because that's what it is here. If one was a liquid, they again wouldn't be able to cancel. So our carbons will not cancel out. Our oxygens will cancel out because again, this is a gas. Okay, and what we're left with is C graphite going to C diamond. That's what's left over. Okay, now once we've had that done, let's look at our delta H's. What did we do to the first reaction? Well, we left it alone, so we're going to leave our negative 394 alone. What did we do with the bottom reaction? We flipped it. So we're going to take our negative sign and flip it, make it a positive. Now all we have to do is add these two reactions together. So negative 394 plus positive 396. Okay, and what's left over is basically just 2 kilojoules of energy. So it takes 2 kilojoules to go from graphite to diamond. Okay, let's keep looking. Okay, next one. What I want you to do is I want you to try this one on your own. This one has a lot more steps, but it's not that complicated. Think of these as a puzzle. They're not too bad. Figure out what you have in your original reaction. Figure out what you're given in your steps and how you want to rearrange the steps to get rid of the stuff you don't want and to keep the stuff you do want. And remember, you want to watch what sides they are on. Okay, and we'll come through and do this one together in just a moment. Okay, so let's go through and look at these reactions one at a time. First and foremost, I notice my boron is on the reactant side here. This is the reaction I want to make. Boron is on the reactant side, and I notice it's over here on the reactant side, and I also notice there's no other reactions with pure boron. So I'm going to want to leave this reaction just the way it sits for 2 reasons. First off, I have my boron on the reactant side. Second off, I have 2 borons over here. So I want to keep this reaction the way it is, which means this delta H is staying the way it is. Okay, my next reaction, what do you notice is wrong with it? Well, my B2H6, which is on the product side over here, is on the reactant side here. And again, I have the same quantity, but I need to flip the reaction. So what I'm going to end up with in this reaction, and I'm going to line up my arrows, and actually I'll rewrite it down here because sometimes it's a lot easier to rewrite stuff, so it's up to you. I always find it a little bit easier to reorganize everything. Okay, so I'm going to rewrite that reaction again with my arrow being my base point, so 3 oxygens and B2H6 becomes my product. And then on this side I have B2O3 and 3 waters. Okay, so this top reaction has a delta H of negative 1273. The bottom one now has a positive 2035 because we flipped the reaction, we're going to flip the sign. Okay, from there, why do we have these excess reactions here? Well, that's to cancel, add up, and do everything else we need to get the rest of this and to get rid of everything we don't want. So how do we do this? The first thing I want to call your attention to is the hydrogen gas on the reactant side. We have no hydrogen thus far, so we need to throw that in here and make sure we're able to cancel everything out to get that. Also keep in mind something that I didn't do, what I should have done. Whoops. There we go, is pay attention to the states in matter. So this water is a gas, and the reason I'm telling you to pay attention is notice the liquids and gas here. That means we may have to use those a little bit later on. States in matter is going to be important because we have 2 different types of waters. We have both liquid and gaseous water. So the next reaction, notice my hydrogen. It is on the reactant side, which is where I want it, but what's wrong with it? There's only 1. So what I'm going to do is actually multiply this whole reaction by 3, and I'm going to leave it the way it sits. Otherwise. So 3 hydrogens plus 3 half oxygens, and I'm going to get my arrows all lined up again, goes to 3 liquid oxygens. Okay, and again, the reason why that's important is because notice, not oxygens, I'm sorry, 3 waters. Notice these waters are not going to cancel out. 3 are gases and 3 are liquids, so we're still not quite done yet. Okay, so now we have to use this next reaction to cancel out what we want. Okay, so kind of go through and see what we have. First and foremost, we have our oxygens here. We have 3 half plus 3 half. We have 3 oxygens over here as well. So that's going to, 3 halves and 3 halves are going to add up to be 6 halves, which is 3. And 3 oxygens, those are going to cancel out. Our B2O3s are going to cancel out. And we're going to be left with what we've set, or what we have here, the 2 borons, the 3 gaseous waters, the 3 liquid waters, and then also our 3 hydrogens. and our B2H6, if you just kind of go through and look at that. So what we want to do is get rid of the waters. Well, we have gaseous waters on the reactant side, liquid waters on the products, and we have no waters in our original reaction, so we want to get rid of them completely. So this reaction we're going to leave as it is, because liquid is on the reactant side, and we'll cancel out the liquid on the product, but we're going to multiply it by 3 as well. So 3H2O liquid going to 3H2O gas. Okay. And also what we didn't do up here, we need to take these numbers. So the first number of negative 286, we did not flip the reaction, we left it the way it stands, but what we need to do is triple it. So 3 times negative 286. And that's going to give us a negative 858. Okay. This next number, 44, we're going to need to triple as well because we tripled that reaction, and that's going to give us a positive 132. I'm not sure why I didn't put the 2 there for the diatomic hydrogen, but anyways. So now let's look at it. We have our 3 gaseous oxygens, or sorry, 3 gaseous waters are going to cancel out. Our 3 liquid waters are going to cancel out. 3 halves plus 3 halves is going to make 6 halves oxygens. Our 3 oxygens are going to cancel out with the 3 oxygens on that side. Okay. The B2O3 is going to cancel out on both sides, and we're left with 2 borons plus 3 hydrogens, going to B2H6. Okay, and jump back up here to our original reaction. Let's double check that that's what it is. 2 borons plus 3 hydrogens forms B2H6. 2 borons plus 3 hydrogens forms B2H6. Now, all we're going to do is take these 4 numbers and add them up. So negative 1273 plus 235, or 2035, plus negative 858 plus 1320. And as long as I didn't type something weird into my calculator, I'm getting a delta H for this reaction to be a positive 1,224 kilojoules. Okay, let's try one more. Okay, again, what I want you to do, pause, try it on your own, see what you come up with. Okay, so let's go through, see what we can do. So this is a reaction we're trying to get up here. Okay, and we're given these 3 steps to get there, or 3 reactions to get there. So let's go through and see what we can figure out. So I see N2H4 and 2H4, both in the liquid phase. They're both on the same side of the reaction, so I'm going to leave this guy alone with the way it stands. I'm going to rewrite it down here, just because, again, sometimes it helps just to have it organized and redone or rewritten. Again, you don't have to. It just kind of helps organize thoughts if you're having a little bit of an issue with it. Okay, the next thing I'm going to do is look at the next reaction. So I see my NH3 and NH3, and it's written where I want it. I don't have to rearrange it, and I have the right quantity. So I can draw my arrow, 2 NH3, 3 hydrogens, and a N2. Okay, next reaction is really going to be used to get that hydrogen here, but I also have hydrogen here, so keep that in mind. What I may want to do is use these other 2 substances as a way to figure out how I want to write this reaction to cancel out as needed. So I know I don't want my CH4O in this reaction because it's not in this one, so I want to cancel it out. Well, right now they're on the same side. They're not going to cancel out. So I'm going to rearrange this, and I want one of my CH4O and CH2O because that's all I have in my original reaction as well, or in the other reaction. So I'm just going to rewrite it as CH2O plus hydrogen, okay, going to CH4O. Now let's see what we end up with here, okay. N2H4 is going to stay, CH4O is going to cancel out, CH2O is going to cancel out, N2 is going to cancel out, 3 hydrogens are going to cancel out, and what we're left over with is our reaction, which is the N2H4. I'm not sure why I just wrote a 2 there. Let's try that again. Sorry. N2H4 plus H2 going to 2NH3. Okay, now these 2 reactions I left alone, so I'm going to leave their values alone, so negative 37 and negative 46. The bottom reaction I flipped, so I'm going to make that a positive 65, and now I'm just going to add those numbers together and see what we come up with. Okay, and we should get, again, as long as I typed everything correctly in my calculator, a negative 18. Okay, if you want to do another one, you can. Okay, here's this guy. Go through, see what you can do, and we will start with this one on the next video. Thanks, guys.